So 11.5 is about Lorentz expansion, but we first talked about Taylor expansion as this kind of motivation, how we extend Taylor expansion to Lorentz expansion. Okay, and last time we already started, but it might sound a little bit like overkill right? to do all the loop integration to get the expression of Taylor expansion, because I'm sure you learned about Taylor expansion before, right? So now using complex or real is just the same. The Taylor expansion is just sum over n from 0 to infinity, just 1 over n factorial, and derivative of that, and evaluate at certain point you want to do the expansion, and then multiply by z minus d to n power. Right? That that you learned about this right in calculus, right? So I mean, if you want to write out explicitly, it's just 1 plus f prime as c sub 0 minus c sub 0, and then f double prime is second derivative of 2 as evaluated as c is 0, c minus c 0 square, and later, and then there will be a general term like that, evaluated as c sub 0, c minus c sub 0, n power, and then the higher order term, right? And to see how this is correct, I mean, not exactly to prove it, but to see how it's correct would be straightforward, right? Last time, I think in another context, we already showed that if you want to know the coefficient of the n power term, so you call this a sub n. This coefficient is a sub n, right? This a sub n times e minus c sub 0 to the power n. We want to calculate this a sub n, and last time we already have the formula, right? Remember how we saying that? You still remember I talked about that? So basically, you will take the n derivative, and we already have that. If we don't have the form of the Taylor expansion, just call it a sub n. This is a sub 0, a sub 1, a sub 2. With this a sub n, in order to get the a sub n, all you need to do is to do n derivative and evaluate that derivative at c sub 0. Because when you take the n derivative, all the terms in front of this term, we have the power c at most c minus sub c sub 0 to the n minus 1. And you take n derivative, will kill all the terms. You know what I mean, right? These are all power functions. So they are at most n minus 1 power. And n derivative will automatically kill all the terms in front. And all the higher order terms will still have at least c minus c sub 0 in front of a factor in front of all these terms. And you evaluate z equals to c sub 0, we kill all the higher order terms. And they will leave you only the constant term, because this one, you take the n derivative, will give you n factorial, which cancel this one, right? Cancel this one, and then cancel all the power. Becomes 1. So only leave you n factorial. So a sub n is given by the n derivative divided by n factorial. With that's how you get how you see that the Taylor expansion is correct, right? That I mean that's seems to be easier than what we talked about last time. But what we did last time on the complex plane is not just to recover this formula. Instead, we wanted to do one step further, because Taylor series is useful only if it's convergent. If it's not convergent, then you write down a series that's no use, right? So we want to know how far away from c sub 0 that you can do the this series is convergent. Okay, and that we consider a generic case. So any point c sub 0, you want to take the series, expand about this c sub 0, but you argue that there is a singularity somewhere, and then the closest singularity we call c sub 1. So there's this distance. The distance is the magnitude c sub 1 minus c sub 0. So that's this distance. And obviously, you choose as a circle centered at c sub 0, draw a circle around it. Right? If the radius of this circle is less than the distance between c sub 1 and c sub 0, then the function f that you try to do an expansion is analytic over the whole region, right? Then for any point that you try to do a expansion, try to evaluate a series of like any point z, right? Then by the Cauchy integral formula, fc is just 1 over 3 pi I. And now integrate over this circle, right? And let's call it c. And then the step, and you want it going around this loop. There's a direction, counterclockwise direction, and this loop integration is in the integration variable is d pi, right? And the denominator is c pi minus c that you try to evaluate at any point c, right? Right? And you require z to be within the interior of this circle, right? So the distance from z to c sub 0 should be less than the radius of this circle, which is c pi minus c sub 0. Okay, and you try to do expansion c minus c 0 in the power of c minus c sub 0. So basically, you do the trick of like subtract c pi minus c sub 0, and then add add the same thing, which including in the minus sign becomes c minus c sub 0. Right? You just add something and subtract something, so that doesn't change anything. But the idea is that c pi is on the circle, so this distance is the radius of the circle, which is always larger than the distance from z to c sub 0, because z is in any point in the interior of this circle, so the distance to the center is always less than the radius. Okay, so you can do an expansion, which is convergent. So basically, take this out, or take this out of the factor, and do a 1 minus z minus z sub 0 divided by c minus z sub 0. Now, okay. Then you use the expansion that I talked about it last time. The one, this is either real or complex is the same. This is just 1 plus z plus c squared, or the high power. Or you can say this sum of n from 0 to infinity, z to the n power. Right? You know this way. Is it not familiar? Anyone is not familiar with this? Can you see why this is so immediately? Why this should be? why this is correct, why this is, anyone is not, anyone cannot see this is correct? You know, no, you cannot see that. Right. Not obvious, yeah. The quick way to see it is just multiply both sides by 1 minus c. You check 1 plus c squared plus everything multiplied by 1 minus c, and check that. So 1 times this one is itself, and then you subtract z minus c times the whole thing. But you can write the subtract part like z times 1 is z, right? And z times c is c squared. So the whole thing is, this is in a bracket, c squared plus c cubed, everything, right? You see that all the other term cancel because of the minus, and subtract this minus that, everything cancel. All the finally just 1, right? You see that? Okay. Okay.
I was confused with that and the binomial expansion.
It's the same. Yeah, you can do that. It's also including binomial expansion. Yeah. It's just one special case of binomial expansion. But, or you can do a tail expansion. It's just like that. But we are going around circular logic. But that doesn't matter. We are not very rigorous here. Okay. Now we use this one. This is now this is your z. The whole thing is your z. And now do just let's just put the summation out. 2.I, and now your f z prime divided by z prime minus z sub 0, and now this is z minus z sub 0 divided by z prime minus z sub 0 to the n out dt prime. Right. I'm just applying this summation for this factor. This is 1 over this one. Okay, and sum over n. Okay, then this factor, the numerator z minus z sub 0 to the power n, doesn't involve c prime, so you can take that out of the integration. That is sum over n, and the 2 pi r. The rest is just the integration of f c prime dc prime and c prime minus z sub 0 to the power n plus 1. And that is the integration. And you multiply by the factor c minus z sub 0 to the power. Okay, so that is after you do the expansion, it's like that. Now you recognize that if the interior is totally, f is totally is analytic, then we talk about what this value is, right? This is just the Cauchy integral formula to take the derivative of the Cauchy integral formula, and we identify this as this is exactly like this one. This is just so n. This is f, and evaluate f to the n derivative. Evaluate as I should say z0. Evaluate z0 divided by n factorial. Okay. Now, so the last step require that is analytic. If you're not analytic, you cannot do the last step because this is from the Cauchy integral formula. Okay. Now, if they're analytic, you can get that, and this is exactly the form of the Taylor expansion, the Taylor series. Okay. So you can now regard this as the proof or a derivation of the Taylor series. Okay. But we want to generalize that now, or consider another case. So this requires F to be analytic over the interior of a circle. And yeah, one more step we need to talk about this. this is all within this circle C, but we already assume this the radius of this circle is less than the distance from Z sub 0 to the closest singularity. So you cannot get C beyond C sub 1. You cannot consider C the radius going past this distance to this nearest singularity. So if you do that, then obviously this will fail, because then Z sub 1 is within this consideration, and you cannot do that because we assume we already used the fact that the integral should be an integral. And if we go beyond that, if this radius of C go beyond this singularity, then you already violate the part of the derivation. Okay, so you cannot do that. And another thing, another word is this treatment is convergent only when this distance C to C sub 0 is less than the distance from C sub 0 to the closest singularity. So that's that we call the radius of convergence, or the range of convergence. Or the whole thing is called distance of convergence. Okay, but that gives you an idea when, the condition where a Taylor series is convergent, as long as it's still within the distance. So this C minus C sub 0 that is still less than the distance from the closest singularity to the center of your expansion, then the series is fine. But if you go beyond that, C minus C 0 has the distance greater than the distance to the closest singularity, and that the series will be divergent. And this is in the complex plane. I mean, this is, you may want to evaluate a function along the real axis, which is not singular in this case. The singularity is somewhere in the complex plane. But it's still true that, say, if you want to evaluate the C sub 0 is actually on your real axis, if this is a real axis, and the singularity is somewhere on the complex plane, the Taylor series on the real axis is still, the range of convergence is still given by this radius. You cannot go beyond that. Even along the real axis is not singular. And this is you need to go to the complex plane to see this fact, because if you go beyond this, then this derivation doesn't go through. Okay. Okay, so that's give you one information that is not available when you just do a direct derivative to check the Taylor series.